ChatGPT solved the arrays and hash maps Leet Code problem in 3 seconds. Clean code, optimal complexity, edge cases handled, big O analysis included. So what exactly is your job now? Here is what ChatGPT did not do. Look at PhonePe's UPI system, 500 million transactions a day, and say hash map, not an array scan. Because the 1 millisecond latency budget makes idempotency checks physically impossible, otherwise, that judgment call made before any code is written is the one that prevents a customer from being double charged. After this video, you will be able to make it and explain exactly why. That is the skill that survives. 5 things you will own after this video. Why an array collapses under PhonePe's load with exact numbers, not theory. How a hash map gives big O of 1 access and why the space trade-off is trivial at scale. The exact Redis implementation, HSETNX, and the atomic operation that guarantees a transaction is processed exactly once. The trade-off AI misses when asked to design this, and the survival skill, naming the constraint before naming the structure. If you watch this video to the end, you will be able to answer an arrays and hash maps interview question better than 99% of candidates who have been building software for years. Let us start with what breaks. Imagine finding a specific receipt in a massive filing cabinet by looking at every single paper from the front. That takes forever. That is exactly how an array scan works for idempotency checks. PhonePe processes 500 million UPI transactions a day. To check if a transaction ID has already been processed, maybe the user clicked pay twice due to bad network. The system reads from the first record to the last until it finds a match. We call this big O of n, linear scan. The UPI gateway routes to the transaction service. If the transaction service uses an array, it loops through millions of recent transaction IDs for every single payment attempt. At PhonePe's traffic, 20,000 transactions per second during peak hours, the service is running billions of comparisons per second before a single rupee is actually transferred. Worse, the transaction records live in PostgreSQL. Every payment attempt fires a full table read to check for duplicates. At 20,000 transactions per second, each one triggering a full table scan, PostgreSQL collapses instantly. The array approach breaks at PhonePe scale before you even build the core feature. This is the problem that forces a different data structure, not because arrays are conceptually bad, because the 1 millisecond latency budget for idempotency and the massive scale make big O of n physically impossible. Instead of reading every receipt in the cabinet, imagine a system that instantly tells you the exact folder number based on the transaction ID. No scanning, no looping, that is a hash map. A hash function takes your key, the unique transaction ID, and calculates the exact memory address where the status lives. Lookup, insert, delete, all big O of 1, constant time regardless of how many millions of payments are happening. Now here is the part most engineers do not pause on. At PhonePe scale, big O of 1 is not just faster than big O of n, it is the only answer that fits inside the 1 millisecond latency budget. Big O of n at 10 million recent records takes seconds. The UPI gateway will time out. Big O of n is not slower, it is structurally impossible. For idempotency, we rely on specific operations. HSETNX writes the transaction ID, but only if it does not already exist. HGET reads it. Both are big O of 1. The HSETNX is the critical one. It is the atomic operation that prevents two identical payment requests from both succeeding at the exact same millisecond without needing a database lock. And expire automatically cleans up the cache after 24 hours, keeping memory bounded. Hash maps trade space for speed. Big O of n memory for big O of 1 time. At PhonePe, 500 million transactions a day means 500 million keys. Each key and status takes roughly 40 bytes. Total 20 gigabytes in Redis for a system that processes billions of rupees and handles the entire country's payment infrastructure. 20 gigabytes of RAM is not a trade-off. It is free. That is the constraint-based reasoning that separates a developer from an engineer. The developer sees extra memory. The engineer sees trivial cost for the only structure that fits the latency budget. Now, how does PhonePe actually wire this up in production? Let us look at the flow. PhonePe stores recent transaction IDs in a Redis cluster. The key is the unique transaction ID. The value is a simple integer representing status, initiated, success, or failed. HSETNX guarantees atomic insertion. No database lock, no mutex, no complex transaction blocks. Two concurrent network retries for the exact same payment are serialized by Redis itself. One succeeds in setting the key, the other receives a zero and is rejected as a duplicate. That design decision eliminates double charging. A customer initiates a payment. The app sends a post to the UPI gateway. The gateway checks the auth token and routes it to the transaction service in under 1 millisecond. The service immediately hits Redis, one command, HSETNX transaction underscore ID. Redis answers in under 1 millisecond. If it returns 1, this is a fresh transaction. The order proceeds to the database. 0 SQL table scans. 0 latency budget consumed on database I/O for duplicate checks. Only after Redis confirms the transaction is unique does the system write to PostgreSQL. If this kind of judgment call, picking Redis HSETNX over a SQL query because the 1 millisecond budget demands it, is what you want to make confidently. Subscribe now. Every Saturday, one DSA judgment call free. Array lookup is big O of n. A full scan through millions of daily records takes seconds. PhonePe's idempotency SLA is 1 millisecond. Array is not slower, it is thousands of times over budget. HashMap calculates the exact memory address from the key and jumps directly 1 millisecond always. That is the correctness boundary. At 20,000 transactions per second, an array in PostgreSQL means thousands of full table scans per second. PostgreSQL collapses. Redis with 500 million HashMap keys handles the volume gracefully using 20 gigabytes of memory. The database is shielded from duplicate noise. If a user has a spotty network and the app retries the payment 3 times in the same second, an array in PostgreSQL requires a transaction lock. Select for update, creating a massive serialization bottleneck. Redis HSETNX is atomic, no lock. The retries are handled in the same 1 millisecond window and only one goes through, zero overhead. Ask an AI to implement duplicate detection and it often generates a SQL query. Correct result, correct logic, but it completely fails the latency budget in a high throughput system. AI defaults to correctness. The engineer defaults to constraint. That gap is the judgment call this entire video exists to teach. The answer is the 1 millisecond budget makes every alternative impossible. Let us put it all together. Here is the complete flow. All components visible. Hop 1. The app sends the payment request or an automatic retry. Hop 2. The gateway authenticates and routes to the transaction service. Hop 3. The service immediately attempts an atomic write to the Redis hash map using HSETNX. Big O of 1. Hop 4. Redis returns 1 if it's a fresh transaction or 0 if it's a duplicate retry, all in under 1 millisecond. Hop 5 only if it was fresh. Does the service proceed to write the heavy transaction payload to PostgreSQL? Hop 6. Customer sees the green checkmark instantly. No double charges. 45 minutes, blank whiteboard. Most candidates start drawing boxes immediately. That is the first mistake. Phase 1 is clarifying constraints. Ask for the transaction volume and latency budget before you even mention a data structure. Phase 2. Propose the naive array and SQL approach. Run the math to show why 20,000 transactions per second causes a database collapse. Prove you know why it fails. Phase 3. Introduce the hash map. Explain how big O of 1 meets the strict 1 millisecond latency budget. Phase 4. Concurrency. The interviewer will ask what happens if a user taps pay twice. Your answer involves atomic operations like HSETNX. No locks. Finally, phase 5. The trade-offs. Acknowledge that the hash map requires 20 gigabytes of RAM, but dismiss it as a trivial infrastructure cost compared to the catastrophic failure of double charging users. Before this video, you might have just memorized the code for arrays and hash maps. After this video, you understand why PhonePe relies on it to process billions. The engineer who says hash map with transaction ID because O1 fits the 1 millisecond budget and prevents double charges is the engineer who designed the payment system. Everyone else just wrote the code. That distinction is your survival skill. Next Saturday, linked lists and LRU cache. Redis evicts the wrong transaction and PhonePe shows a stale balance to millions. Cache eviction policies decide correctness. That is episode 2. Subscribe to ByteLearn for the complete one engineer system DSA edition. One data structure per week. One constraint that forces the choice every Saturday. If you are a B.Tech student, a fresher, or an engineer wondering what the point of learning DSA is now that AI can grind leet code, this series is the answer. Hit the bell. See you Saturday. Question: which DSA judgment surprised you most? Drop it below. I reply to the first 10.